Okay, Lebanon, for your question. To answer that question, first we start with maybe I use a big one, yeah, so it's clearer later. All right, so that is a wave that you are given. Okay, the displacement of the wave that you are given. So I'll be using 15 here. So 10, 5. So 5 for each half wave here. Okay, and then I'm going to use 2 of this distance. Okay, so this one I extend a bit, this one here also. Now I have 2 of this thickness of my ruler to represent the amplitude of the wave. Okay, amplitude of the wave. And this one here is our distance from the sound source. Okay, from the source of the wave. And the vertical axis, okay, this one is the delta x. Well, this delta x refer to how far is that air molecule moving away from equilibrium position. Okay, that's the one. So the positive side is moving away. Okay, the air molecule is away from the source. Okay, and then the one negative here is moving towards the source. Away, this is a source here. Okay, the source is along this axis, and then if it is air molecule moving to the right hand side, is positive, so it's away from the source, so your graph will be up here. And then if the air molecule is moving towards the left, then it becomes negative this side. Well, the positive negative can actually be chosen different or depend on the preference. And then this one here is towards the source. Okay, towards the source. Okay, so that is our reference line. This is the reference line, lightly drawn here also. And then this will be our guideline for the total wave. We have 3 of it, right? Okay, and then here you have maximum, and this one is a minimum, and then you have the maximum again here. Right, so you have 3 points which refer to 2 maximums and also 2 maxima and 1 minimum. Okay, 1 minimum. So now we're going to draw the wave. Okay, it's going to look more or less like this. Okay, here the negative side, and this one. Alright, so not that pretty. You have this point given to you, point A, point B, point C, and point D. Question asks you to find where is a compression point, right? Okay, the first thing you do is draw a series of lines. Okay, a series of lines that will help us to identify how the air molecule move. So your line should be starting from the source until where the graph ends. Alright, this is a point, ending point. This is a starting point. So we need to have an initial condition. Okay, this is the initial condition. This line represents the position of the air molecule when there's no wave passing through, no sound wave passing through. So the location of all these waves, okay, we strategically we choose this important location here. Here, this is a one, and another one here. Okay, later we extend downwards. Okay, we can actually draw it now here. So start from here downwards, then we have here downwards, and then important one, this one already have, this one already have, and then the maximum. Okay, the maximum also is an important point here. Yeah, all right, one more line, and then a minimum as well, one more line, maximum again, the next cycle already, this one. Okay, one more line, and then other than that, we choose somewhere in between the 0 and the maximum and 0 and the minimum, somewhere in the center here. So I'll use this one. Okay, this one is 5, right? So we roughly choose in the center. Okay, we just do no need measurement. This one, this one, this one, here and here. So we start from here. Okay, this one will refer to the height here, and then this one as well. Okay, if the graph is drawn properly, you see that the actually the what we call it, the height of the graph should be the same. Okay, it should be the same. And this one here refer to this location, and this one as well. Here, this one much better, almost the same height. Supposed to be the same height. Okay, and then the next one here. Then the last one, this one. Okay. Okay, now we have how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So we have 13 line. This line represents 13 molecules. Okay, 13 A molecules. Original position of the A molecule when there is no sound wave passing through. Okay, when there's no sound wave passing through. What happens when you have sound wave pass through? When you have sound wave pass through, for example, the energy transfer are in this format. Okay, the intensity changes like that. So you can transfer into the movement of the air molecule. So here, this is T is equal to 0, let's say, 0 second, equilibrium positions. Why positions S? Because 13 of them are all at that location without any changes in vibration. We are not talking about the minimum energy that they have. We are talking about what happens when there's no sound wave passing through. We know that all the molecules are like moving in random, but they are vibrating. When sound wave pass through, then is the vibration will be at a larger amplitude. Okay. Now next one is what happens when energy pass through, sound wave pass through. This one here is T at any other value, unknown value. So this one is when sound wave pass through. Okay, when sound wave pass through here. So if you refer to this graph, there are a few locations where the air molecule are still not moving. 1, 2, 3, 4, because they are neither moving away nor moving towards the sound source. So these are the position that it does not change. Here, here, here. Okay, and this one here. All right. Okay, so these are the position which the air molecule does not move. Okay, non-net movement. Now we refer to the maximum movement first. This has a maximum movement. This one has a maximum movement. This one also a maximum movement. The only difference is this maximum movement and this one is moving away from the sound source. So they are moving in that direction to your right hand side. This one is moving to your left hand side. Okay, we start with this one first. So second. So first you start with location where these are no movement. Okay, and then you go to this A, C, and this. I'll call this one E. Okay, so A, C, E. So we choose that location. So this one is the delta X is the largest away from source. So this air molecule here is moving with the largest amplitude to the right hand side. Okay, so I will use red color, okay, to represent the movement. So it's maximum, movement is maximum here. So I draw maximum. How far is the maximum I can move? Let's say move up to the position here. Okay, here. This is how your air molecule move now. So that means this air molecule is going to move to that location here. Okay, and then another one here. This one also moving maximally to the right hand side. Okay, so you have to trace. Okay, where does that molecule move here? So you can actually name them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. This is 1, no changes. And then 5, also no changes. And then 9, also no changes. And 13, also no changes. Alright. Okay. And then one more. This one here, what happened? This one is maximum, right? Towards the source. Towards, that means it go to the left hand side. Okay. So go to the left hand side and use blue color. So now we have a molecule which is moving to the left hand side. This one, number 7. So number 7 now is moving to the left hand side. Okay, so blue color. So I can actually still use a red color if you want. Okay, but just to make the difference. So this one is moving now to the left hand side. So now you have a molecule here. Okay, so now we have done for the maximum point and the minimum point. So you label that A molecule so that you don't get confused. So this 1, this is 5. This one is from where? This one is from number 3, right? So this is molecule number 3. This one is from where? This one from number 7. So this is molecule number 7. This one is molecule number 11. Okay, 11. Okay, we have done this one. This location done. Done, done, done. And this one also done. Alright. Okay. Now, you can actually, now you already know where is your answer already. Which one is compression? Compress when forces or movement are towards a single point, right? So actually supposed to be this one. So your answer should be B. Alright. But before that, before we get the finalized answer, we want to do the compression sorry, the displacement of the air molecule in more detail. Now, this one already done. Okay, now we look at the positive side. Air molecule that move away from the source. How about these two? Molecule 2 and 4. They are still moving to the right hand side, right? But they are not moving that much, you see or not? You see, this is how much they are moving. This one is very much. This one is not that much, so our arrow should be shorter for number 2 and number 4. See or not? So our number 2, okay, number 2 here is moving. The arrow should be shorter. Okay, arrow should be shorter. So air molecule number 2 will be here. Okay, will be here. Now, how about number 4? Okay, number 4 is also not that much. Okay, not that much. So you can see that they are actually the same height, right? So our molecule number 4 is also moving like that. Okay, so this is the location of molecule number 4. So after you finish everything, just make sure that you have the same number of molecule. Like for example now, 1, 2, 3, 4, 5, 7. That means there must be 6 somewhere here, right? Okay, now look at number 6. Where's number 6? Molecule number 6 is here. See or not? 6 is in the negative side. So we have towards the source. That means that molecule moving to the left hand side. So now, because the magnitude is smaller than this one, so the arrow that you're drawing should be shorter than this. That is this position number 6. So position number 6 supposed to be here, but because it has a little bit of motion, okay, move to this one. So the direction of the arrow should be here. And this is your molecule number 6. So now we completed one side already. See or not? Now, okay. 1, 2, 3, 4, 5, 6, 7. So copy, continue with the rest. Okay, now what happened to this one? We already have finished number 7 up to 7. Now we go to number 8. Okay, what happened to number 8? Number 8 is still negative, right? Still negative. The displacement is the same like this one. Same like this. So our number 8 also move this much. Okay, with the molecule number 8 here. Okay, molecule number 8 here. Okay. Done. Number 9, not moving. Number 9, not moving. And then what happened to number 10? Again, number 10 is moving away from the source. The same arrow like this one and this one. So we refer to this is molecule number 4. So here, this much here. So I'm going to draw using red color again. So this is number 10, right? Number 10 moving that much. Not that much. Okay, not that much. Shorter than this one. So this is our molecule number 10. So we have molecule number 10, 11, 12. Where is your 12? Your 12 have the same amplitude as your number 10 in the same direction. So we draw that same arrow here. Okay. So there is your molecule number 12. Okay. So after you completed everything, you can check out that one already. Okay, you can check for you see this one here. You look at how the arrow behave. The 2, 3, 4 and also the 10, 11, 12. They are the same, right? Why they are the same? Because they are repeating already. So if you keep going on drawing another cycle, you get exactly the same pattern like that. Duplicate. Okay, one after another. Okay. Now, when you completed this diagram, okay, it's very clear that this A molecule is actually moving towards this direction. The rest of the molecule here is moving towards this direction. So this point here, okay, now you look at this point. What is this point now? This area is compression. Okay, compression. And then whereas the opposite side, this area here, because a molecule is moving away, right? Moving away. So this area is rarefaction. What is rarefaction? Rarefaction is actually quite the same as tension. When you push something, the force is towards that. But for solid object, we can use the word compress and tension. Okay, but for air molecule, you cannot pull air, right? How can you pull air? It's not the movie Airbender, right? No? So you cannot pull air. So what happens is we have a specific words where air molecule are moving away from each other, creating a pressure that is slightly lower than the atmospheric pressure. That area is called rarefaction. The word rare means less. Okay, rarefaction. Okay, compression is easily understood because we know that gas can be compressed. Okay, so compression and rarefaction. So this point here is a compression point. And then where is your point number 9? Number 9 here, this one is a rarefaction. Okay, rarefaction. Okay, so clear? All right, clear, right? Okay.